Hi again. How was the week?
It's nice.
Good. Did any of you get the chance to start thinking about these posterior updates? Yes? Did you manage to have some basic implementation going? Or not? I can go through it myself, but how many of you have tried? Let's want to see. Okay, let's do. Okay, you can now let's go through it all together. Okay. So just to remind you what we're going on about, we talked a bit about what is Bayesian inference and what's probabilities. Just to remind everybody, you should already know this, but we wanted to kind of remind people of what it is. And something that you might not know is the Bayesian idea of how you learn. Okay. So the basic idea is you have a few hypotheses. Either one of them might be true, but you have some prior belief about which one might be true. It's a number telling you your confidence about every possible model or hypothesis. And then given some data, then you increase or reduce these probabilities. And we have given this example of John being a medium and have two different models. One where John is able to perfectly predict something, and the other where he's not really better than chance. And in that particular example, it's pretty easy, right, to actually calculate what is the probability of John being a medium if we have actually observed him correctly predict a number of tosses. Yeah. So we can even write this down if we want in closed form, because we know that the probability of randomly saying yes when the coin is coming heads is half, and anyway the probability of randomly predicting the coin n times has to be 2 to the power of minus n, right? So let me just go through that a bit. Since okay, well, hope it works. Right. So what you have basically is you have two models, and one model says that John is a medium. Okay. So then if he correctly predicts n times, okay, x now is where he correctly predicted, this has the probability 1, because under the model where he is an actual medium, he has to always predict perfectly. Okay. So the probability that he incorrectly predicts sometimes, for example like this, has to be 0 under the model where he is an actual medium. Okay? And the other model where he's not a medium, we say that any possible sequence of observations, like for example this one, has the same probability, and it's always going to be 2 to the minus n. Okay? And that way everything will sum up to 1. So that means that if we start from a specific prior for him being a medium, yeah, then we can calculate the posterior given some observations by simply looking at the probability of these observations under this model. Okay, and then dividing by the same thing for the first model where he is a medium, and then for the second model where he's not a medium. Okay, so this is all that you need to be able to do if you're doing Bayesian inference. You need to be able to calculate this product and then divide by this sum. This is very trivial when you have a finite number of possible models, and in your exercise you should have been able to start doing it. And it just becomes more complicated in the general case when things become really interesting. Okay, so now for this particular example, as long as we have just any sequence where there is a single 0 where he failed to predict once, then this will become 0 here. Yeah. So that means that the probability that he's a medium, according to our belief, will be 0 if he just fails once. If he doesn't fail for n times, then let's say n successes, then what do you get? Then you get that this is 2, no, this is just 1, sorry. And then you have whatever you selected here as your prior for him being a medium. Let's call this P. and then here you have the same thing, 1 times p, and then here you must have 2 to the minus n, and here you must have 1 minus p. Okay? So basically what you see is that as n goes to infinity, right, this converges to 1, so you become more and more sure that he's a medium. Okay? And of course, maybe you're not really sure that he's a medium in the beginning. You say, well, the chance that they are a medium is very, very small, so maybe this p should be very, very small. So maybe you would like to have p something like 2 to the minus k, where k is a big number. So let's say 1 in a million, so it's going to be like 7 or something. Okay? So then you end up with something like this. And this one is approximately 1. If p is very small, then this is basically almost 1. So you have this kind of fraction here. So it's minus k, and then here minus n. So then what dominates is basically how much strength you put in your prior that is not a medium. So the larger the k is, the more you believe it's not a medium before you see any data. And the n is the number of data you have seen that seem to prove that he's an actual medium. Okay? So that's the basic idea. Now I would like to extend this to the problem where we had before, where we had a meteorological station, so it's a slightly more complicated scenario. Okay? But that's fine. Now we have a number of stations, and for every station we have a prediction of what is going to be the probability of rain, and then we actually observe the rain. Yeah. And now the basic question is, how are we going to create a simple way to update after every day of observations, to update our belief about what is the right station. Okay? So here the assumption is that there is one station that is the best model, or in some sense there is one station that is whose model of the rain corresponds somehow to reality. Okay? This might not be the case, of course. It's not like the rain comes depending on the predictions of some specific weather station. But we know that under some conditions, what we will converge to is the station with the best performance overall, okay? Which is good enough for what we want. And if we assume that the performance of the stations doesn't change over time, so they are always equally good when time passes, then we have a nice model. Now, how does this model work? It's slightly more complicated than before, right? Because here we say that every station makes a new prediction, of course, depending on what happened in the past, right? So they don't just have a model that says randomly tomorrow it's going to rain, tomorrow it's not going to rain. So they see the historical data and they say something's going to happen next. Okay? So how are we going to solve this? Well, we do have, I do give you the solution for this, how you're actually supposed to do it. But actually it might be instructive to spend a little bit of time thinking of why this is the right formula, if you want. Does anybody want to do that? It's not necessary for understanding at a high level this material. So, just jump back to the notes. Okay. This doesn't quite fit here. Okay. So what we have is, when we say we have the posterior distribution of something, right? We have the probability of the model given all the data, right? Yeah. So what we would like to write here is, when we write here the probability at time t, we basically mean, right, the probability of the model under our prior distribution, this is just a definition, given all the data that we have seen so far, okay, and all the predictions that the models made. Okay, that's the idea here. So let me just switch that over. Okay, you can see it. Maybe it needs to focus somehow. Okay, now it's a bit better focused. So what you have here is the probability of the model, given all the previous observations, is basically defined to be this index things here. So we just say our belief at time t is just our posterior distribution for the model conditioned on all the previous observations. Okay? Fine. So what does this mean? Well, if we know how to write this, right? So we write the probability of this guy, right? Now, how can we write this? We can write the probability of all this data, right? And all the predictions under one model, yeah? And then predictions of this model. Okay. Now, the interesting thing here I'm adding all the predictions of all the models, right? And this is the actual thing that happened, or the other way around. I forgot how I mentioned it. So, why is the prediction, right? Okay. So what you see here is that the predictions are kind of dependent like this. That's fine. But now what we'd like to do is mention that, well, the ith station has prediction yi, okay? And the thing is that the predictions of that station don't really depend on the predictions of the other stations. They only depend on the data, yeah? And they only depend on the previous data. Yeah? So then you basically can rewrite this in terms of the things that you depend on, okay? So let's make it for one station. So X is the stations and Y is the station. Y is the actual things. So X are the station predictions. Fine. So this is just that. Okay. So we don't really care about. Sorry. The predictions are Y. The predictions are X. So this is just the data that you see. Okay. So the models of the stations just tell you what's the probability of rain. You don't really care about the predictions of the other stations. And the other thing you can do is you can rewrite this as this. Okay. Sorry for the confusion with the notation there. Okay. So we use here the basic idea of joint probability, which says PA and B is just PA given B times P of P. Okay. And now here we have rain today, given what happened in the previous days, is just times the probability of what happened in the previous days is the same as the joint probability of all the events in the previous days and today. And you can just write this recursively to have, in the end, probability from 1 to t of probability of yt, yi, given y1 to yi minus 1. Okay? And then the last one just is empty. Okay, for y1 we have from y1 to y0, which doesn't exist. So just to make it clear, we just write times like this times probability of y1. Okay, and there's no dependence on what the predictions of the other models are. Every model just predicts the rain, and there is no other dependence on anything else. Okay, so here we have other predictions. We don't care. And here you have actual rain, okay, or not rain. So now if you repack this definition, then you get what we have here on the slide, right? Because now for every point time in t, now if you repack this definition, you basically get this idea, which is probability of yt given y1 to yt minus 1 times ct minus 1 of mu, okay? And there are some constants here that I don't add, which are the denominator and the fraction, okay? But if you work it out, you will see the same thing is happening. So there are basically one step to do this. So the posterior is just defined to be conditioned on all the data. The predictions of every model only relate to the rain and not the other model's predictions. Then we can use the definition of joint probability to factorize this distribution like this. So the joint probability of rain until now is basically the rain today given rain before for all days of rain, and then you factorize this into having the rain up to time t minus 1. Then you can write this as a product, which is fine, and every term in this product is what we had in the slide. Now the tricky part is to recognize that each one of these terms corresponds, if you put them together, corresponds to the belief at the previous step. And then you have this formula here. Okay? And the nice thing about this formula is that basically it tells you, well, it's pretty simple to update your belief. You look at every model, you look at the current belief, you multiply with how well the model fits, and then you normalize. So it's very intuitively, it's very simple. Why it's correct, I try to show you now. And there are many, many other algorithms that do this more generally. You can think of having, you're betting horses, let's say, okay? And there are 10 different betting companies that tell you bet for this horse or bet for that horse. And then you follow the advice of one of these companies, and then instead of saying, I will weigh my probabilities or how much I use the advice of one company based on whether they have been correct, instead you can do it based on how much money you win or lose for its company. And then the same thing still works. So this general update is called the multiplicative weights algorithm, where you have some weights for every model, and then you multiply these weights depending on how well the model performed. And then the better models increase, the less good models decrease. Okay? This is a very, very simple algorithm, and if you have an infinite number of models, it's fine, it's very easy to use. It just becomes complicated when you have an infinite number of models, like most things. Okay. So how does the algorithm work? Let's see. Okay. So how does it work? Okay, so some hints here. First, we would like to get the posterior, right? So we say here that the probability that you get the ith model, right? So the ith model gives you the jth outcome, okay? So probability of data j, right? For model I, for outcome. For model I is just p, right? I outcome, right? Okay, fine. So I'll make it with a for loop just to make it very, very simple. For I in range n models, okay? So we'll go for all the models, okay? Now we have to multiply this guy with the prior, right? Of the model. Fine. Now we'll put it somewhere else. Where should we put it? Let's call this posterior, okay? And that's almost it, okay? We need something else. We need to divide by the sum of this to make sure they sum to 1, because our posterior belief about the correctness of a model is simply a probability distribution, and this has to sum to 1. So to sum to 1, we just divide by the sum of this. So total, let's say, is 0, and let's add this to the total. I think you can do this in Python, right? And there we're almost done, and then is it possible to do this in Python? I don't know. Probably with NumPy. I don't know if this works, but you get what I mean. We can try and run it later. Okay, so let's try and run it maybe. Okay, maybe I should do this some way. Sorry, I have a little problem here. I just want to see this in my screen, and it's somehow hard. I can't. Anyway. Okay, I'm in the correct place. So, and whatever I call this posterior pi. Data type not understood, NP zeros. Are you going to debug this now, or maybe you can finish debugging it later? But line 36. Did I forget to import NumPy? No, I didn't. So why is it wrong? Any idea here what's going wrong? just doing it on the fly, basically. Huh? Any idea what's wrong here? So for t in equal range, for modeling range, prediction is this one, fine. Then I get an error here in data type not known.
Try a second set of parentheses, because I think you want like n model of rows and n outcomes of columns.
Yeah.
But you have to have that like a two. You have to have
Like this, something like
Yeah.
this. Okay. Okay, maybe that's it.
I think you have to do it in the bottom. No. Yeah, but the p further down too.
Line 49.
Yeah, but not like the square brackets, but regular.
Ah, this one, yeah.
Oh.
This one, another thing. Okay,
Okay.
that's another thing. That was wrong, I think.
But with NP zeros.
And then this finish. And then this one has also something that you can fit in, like, but you can fill this in from the example. Did you know how you can fill a table directly with Python? Does anybody know? Random uniform 01 help. Okay. Huh?
Don't remember how uniform works.
No, you have to look it up. But I'm saying that we have a table, right,
Yeah.
in the data, and we can just fill that in. I guess we can just say we have 3 models, right?
Yeah.
And then for every model we have predictions, so just fill some data in, right? So you have 3 models and 3 predictions. Okay. 0.1, 0.5, 0.8. Do I need commas here? I forget. Or is space okay? Okay. Okay, so now we have, yeah, also between these, yeah. Okay, so now we have the predictions of the models, right? And for every model, and then say t equals 3. Okay. So, okay, I didn't complain now, so probably it's okay. Now, anyway, so here what you have now is the posterior. Maybe this works, it doesn't complain. So check if it works. And once you have this, then you can also use, let's see, you can also use your current belief to get an outcome probability for every possible outcome, right? So here you can again do the same thing. Just some copy pasting here. Okay, models is there. It's called belief here. That's fine. And then we have this one as already 0. So then we just say outcome probability. Yeah, is this one times belief. Okay, fine. Okay, so our models here are described perfectly by this p. Okay, and when we input this p to the system, then we just say, well, give the prediction of the specific model at time t. Okay, and then we have to put them all together in a matrix like this. So then we have a small matrix containing the current predictions of all the models, and then we send this to the posterior, and then we get it, and this should work. And we can also use this one, which basically this is the denominator of the posterior update, but it's also called the marginal distribution because it tells you what's the probability of the data according to all the models. Okay, so I mean it's pretty simple to do. In general, it's not so simple. Because you don't have a finite number of models, or the models are not basically so simple as this one, we just give you probability for n or no rain. But this is the simplest type of Bayesian update you can do. I will save this on the GitHub and you can try and finish it later. Now, Another interesting case is when you have infinite number of models, as we said. So let's take the coin as an example. Let's say you're tossing a coin and you expect most coins to come up heads half of the time. Yeah? But they don't really come exactly half of the time. Maybe it depends on how you throw the coin or the dynamics of, or I don't know, humidity, who knows. So you have a randomly chosen coin, and you have a belief about how close to 0.5 it's going to be. So one way to describe this is by some prior distribution, all these probabilities of landing heads. And there is a very well-known distribution called the Beta distribution that describes this. Okay? And it usually has this shape here. Well, one example shape is like this. So here we are pretty sure it's around 0.5, but it could be anywhere from 0 to 1, yeah, excluding 0 and 1. So here we assume a Bernoulli model for the coin, and the Bernoulli model just means that whenever the coin lands heads or tails, it doesn't depend on the previous throws, and it's a fixed probability, and this probability is theta. Yeah. So that means that the probability of landing n number of heads and this many number of tails is proportional to this. Yeah. There is also a normalization factor, but we don't care about it. Now, let's combine this with what we call the likelihood. Now, we have an infinite number of models. Before we had a finite number. So for every possible model, there is a given probability for this data. And this is called the likelihood function. It's not really a probability distribution, it just says how well the data fits. It's the probability of the specific data for every model. So it can be arbitrarily shaped, it can have many peaks, it can sum to anything. Yeah? So it's not a probability distribution, but it does tell you which is the best model according to the data. Yeah? Now the idea of the Bayesian inference now is basically to combine this curve, which is what you think about the right parameter, with this data-driven likelihood, and get a new distribution, which is called the posterior distribution, that we showed before. But now it's not just a simple vector; it's a complete function. Yeah. So it's the same thing as before. Now the interesting thing about Bayesian inference in this case is that the prior and posterior distributions are described by the same family of functions. And these are called the beta distribution functions. And they only have two parameters, alpha and beta. And I will show you now what they look like, how you use them. I have a little toy example here. So let's see, open a new one. It's easier to use for this purpose. So basically, beta distribution exists in SciPy statistics. You can use it pretty easily. And here I'm just plotting an x-axis, and these are the two parameters for the beta distribution. And here we plot it. Okay. Now if we change these parameters, then you get a different plot. So for 1 and 10, you get something like this. For 1 and 1, we get something like this. So if they are A and B are equal, then the distribution is centered in the middle. Yeah. So if you have 100 and 100, you get something like this. Or if you have 0.5 and 0.5, you get something like this. Okay. So the average value or the expected value of the distribution is 0.5 is alpha divided by alpha plus beta. Yeah. So it's 1 and a half, 1/2. Okay. So the classical way to use this is to say alpha equal beta equal 1. Which gives you the uniform distribution. So you are equally certain before you see any data that it could be something between 0 and 1, any possible number. Yeah, this is uniform. Okay, everybody familiar with the uniform distribution? Yes, you heard the term before? How many of you heard the term uniform distribution before? Yeah, yeah. Okay, good. Just checking. Now, let's say you have a specific number of successes. So you have the medium or claimed medium, and he predicts the coin 7 times correctly, and 1 time he fails. Okay, so maybe you're not convinced he's a medium, but maybe he has a better than average guessing rate somehow. Yeah, and you can try and guess what it is, and you can try and plot this posterior distribution, and it has this shape. Yeah, of course the posterior depends both on the number of successes and failures and the prior you have used. Yeah, so if you are pretty sure that the guesses of anybody have to be around 0.5. then you can use these parameters here. So now your prior is concentrated around 0.5. So you think really it has to be almost random, but maybe somebody is kind of gifted, but it's very unlikely. And then you see here that what you get is you have a very similar curve to before, cannot really distinguish it, right? Now the interesting thing is that for both cases, the beta distribution, yeah, this is here how you plot it, is exactly the same form. I just call the same function to plot it. And the only thing you change is these parameters alpha and beta, or A and B here. You just add the number of successes to one parameter and the number of failures to the other one. And this is how you get the new function. Yeah? And this is perfectly correct. There is nothing strange about it. It just happens coincidentally that for this particular problem, for this particular family of distributions, there is a very simple solution and a very simple way to describe everything. Okay? And this is the only one, the only distribution that we are going to use for you to hand code stuff. Okay? Everything else will be done, I think, with existing packages. But you should understand the Beta-Bernoulli prior and kind of see how it works. So I have these examples here. Yeah. But we will never do anything more complicated than this, I think. Yeah. Okay. So let's go back. I think that's enough for this. And let's continue with the basic problem of making decisions. Okay, so let's say I give you some choices, okay, for food, okay. How many of you would like to eat McDonald's right now? Or you have already eaten, but if you didn't, no. Surströmming?
No.
Oatmeal? Okay, fine. So you have some preference, right? Each one of you, okay? And as the class, you also have some preference. So let's say that if we were going to order now food for everybody, and you have to order from the same place, okay? Maybe somebody's allergic to oats, I don't know, so you cannot order oatmeal, okay? So then you have to find some other compromise. Maybe you can vote, right? Voting is okay. But this is a specific way of selecting something that people prefer, okay? And then money, slightly different thing here, money. So let's say you have a choice between those three things. Which one would prefer, okay, Norwegian kroner, if you like, 10 million Norwegian kroner to 10 million USDs? Nobody, right? Would anybody prefer 10 million Bitcoins to 10 million USDs? Yes, you would? Why?
It's more value.
You think so? You think you'll be able to sell them?
Probably not 10 million, but probably not.
Okay. So another thing about some things when you want them, right, is how much value they will have later, right? So you say, right now you care about eating now, right? So it's kind of simple. But if you talk about money, it's also how you're going to use it later. If you have already 1 million, maybe 1 million more is not so much. Yeah. If you don't have anything, then it's of course a lot, right? And then there's entertainment, which is a completely different thing. It's kind of more about your personal happiness, so it's kind of more immediate reward. But there's all very different types of rewards, and it's very hard to say that you prefer one to the other or if you trade something for another, but we're going to talk here about the utility theory, which says that you can just assign a number, and this number is magical and tells you how much you like things. Okay, so you can think about any combination of these things, and it gives you just a number, and this number tells you how much you like this combination. So if you had a way to choose between any combination of these things or any one of these things, then this number will tell you what you would like. Now the problem is that this doesn't work for more than one person or for multi-criteria, because then you have logical problems. So it could be that you prefer A to B and B to C, but you prefer C to A. So there's a circle. This can happen in elections, for example. Okay? So we will stick with this very simple framework where every choice you have is called a reward. Okay? Even if it's bad, we call it a reward. And there is some utility function mapping from rewards to numbers. Yeah. So how much you like something is how much this number is. So you prefer some specific thing to another thing if this reward has a higher utility than the other reward. Okay? So yeah, this is basically what we already discussed a little bit. Do you think there is a way to define a common utility function? Well, we did discuss voting as an example, right? But then how fair this is kind of uncertain, right? So some people that have a very bad outcome might feel bad about it, right? So let's say that each one of you had a utility for, let's say, the 3 different foods, okay, that we talked about. Instead of counting the number of votes, could you somehow use the individual utility of everybody? Do you think? So if you could assign a number to your individual, let's say, likeness of Surströmming, then and everybody could do the same thing, then there could be a way of saying, if everybody buys Surströmming, then this is how much we all gain by or lose by it, right? So you could say that you just add up everybody's utility together, and then we just choose the thing that has the maximum utility. Okay? But then you have other problems. So say if my utility is 0 for everything apart from Surströmming, where it's infinity. So then we have to buy a Surströmming because that's what maximizes the sum of utilities, right? So there are various problems with this, and this is lots of interesting work on social choice theory and stuff. We are not going to deal with that. We're going to say there is some utility function, somebody gives this to us. At least in the beginning, we'll think of it like that. And then we're just going to maximize it somehow. Okay? Okay. Now, one other thing is, okay, now we defined preferences over fixed things. But what if there was some randomness involved? Yeah. Okay. Why don't you tell me whether you prefer to have 100 euros now or flip a coin and get 100 euros?
100 euros now.
100 euros now. Okay. Why? Do you think it's unlikely? Kick heads.
Yeah. I don't like them.
Okay, that's all. Right. Okay. Okay. What if we change the odds? It's like 1 million, like €1 now, or 1 million euros with 1 in a million probability. So it's kind of the same, right? Yeah.
I would gamble because €1 is nothing, but you have a chance to win 1 million. 1 million is a big chunk of money.
Okay.
So then I would take the coin.
Okay. Okay. That's fine. Right. Great. So we can explain both of these things with the same thing. We don't have to assume anything special that you don't like gambling. You can all put both of these things together by saying that you just care about maximizing the expected utility. Okay? So expectation is basically probability times a random variable. And here we talk about conditional expectations. If you have some actions or choices, and choices are A or B, take the money now or throw a coin and take the money later if you take it. Okay? So this is the expected utility. And if we have this assumption now, then what we would do will depend a lot on what is this shape of the utility. Here there is maybe the assumption in the back of your brain that the worth of the money to me is proportional to the amount of money I get, but this is not necessarily the case. Yeah. So it might be that, as I said, that if you have €1 million, then another million is okay, but maybe if you have $1 billion, then another million is nothing, right? It's like, who cares? So maybe you have an increasing factor, so you would like to have more and more money, but it's not a linear function. It's something maybe that decreases. The curvature is kind of going down. Yeah. So let me just go through this a little bit for the next 5 minutes. So let's say you have 2 possible things that you can do, right? And there are 2 possible outcomes, okay? And this is outcome where you get no money, and here you get 1 million or whatever, 1,000. And here I'm telling you get 500. So you have these choices. Either gamble between those 2 or just choose this one. Yeah. Now, basically what expected utility says is that if this line is your utility function, yeah, then the expectation of this random variable is basically this one plus this one divided by 2. It has to be here. Yeah. If your utility function has this shape that I mentioned before, it's concave. So the more money you have, the better, but not so much better. Yeah. Then when you basically look at how much money you would get, or how much utility you would get from the money, it will be higher than the expected value, which is exactly on this line here. And if your utility function was convex, which corresponds in some way to people that like taking risks, then the value of getting exactly 500 with certainty would be lower than the value of getting 0, 1000 with 50% probability. And this is basically explained geometrically by this. So if you look at the value of taking exactly 500, is exactly the value of your utility function at 500. So there are 3 functions, 1, 2, 3. And depending on the shape of your function, you will have a different choice. So if you say that you don't like risk, then you have a function like this. If you say that you like risk, then you probably have a function like this. And this is specifically something that people use a lot in the financial industry and stuff like that, where they explain risk-taking by saying there is some kind of convex or concave utility function. Specifically for insurance companies, for example, this is probably important because, or banking, you assume that the consumer has a utility function like this about money. So the more money, the better, but it doesn't make a big difference when you have a lot of money. While the company itself, for many different reasons, but also because of other effects, like how much they can loan, they have a linear utility function. So companies look in the long term in theory, they have lots of money reserves, they can loan, have loans, while consumers have, sometimes they have a curve like this. So if they get into debt, it's very bad for them. So you start having problems. You start running credit card debt, you start having overdraft fees from your bank. It's very bad if you have negative money. But for companies, it doesn't matter so much if you have negative money. So they could have basically this almost linear curve. So it's very interesting, this interaction. So that's how basically one way that companies that give loans or sell insurance basically manage to make money. Because for some things you have to be very risk averse, because having negative money usually has a very, very low utility for you. So if you lose your house, you're kind of very, very bad if you have already bought it. Now, I guess this is all for this introduction to decision theory and stuff. So we'll take a short break, and then we'll do a very little exercise about preferring a couple of different things. Again, this is going to be very light today, and we'll do some more technical stuff tomorrow. Again, light on the theory, and you will also work on this. Some of the stuff we talked about tomorrow, we'll work with it on the labs, which is next week. So next week is only labs. Okay. All right. Thanks. See you in a bit.